Okay, good morning, everyone. Ready for the long weekend? And you have big plans, partying, visiting family. How about a quiz? Take home quiz. Nah, enjoy a long weekend. No quiz from this week. Since we already have, we already covered 5 quizzes. My target for the quarter usually is like 7, at least 7, if not more. 7 quizzes takes you right up to like, about 2 midterms. It's equivalent to about 2 midterms in terms of time and the amount of material that's assessed. And so we are still on target for about 7 quizzes. And so, we'll skip one next week. It will be fine. All right. So what I want to do today is cover the rest of the concept of the capacitor. It should go quickly because it's exactly the same as the inductor. The equations are also the same. It's only the quantities are switched. The voltage is switched for the current and vice versa. And then there are 4 examples. I'm going to cover 2 examples, and the other 2 I think I'll post in the slides just because we don't have enough time to cover all 4 of them in class. The homework made it due for Monday night. Most of them are conceptual short answer questions. I think at least 3 or 4 I've already covered, they are based on the material that I've already covered in class. Several students have actually started the homework and also finished it. So even before I completed the examples, because the topic that we are going to look at is also something that you would have seen in your own engineering fields, okay? Because after you set up the problems, it's simply mathematical calculation. And mathematical calculation you would have, already done in physics, in your science classes, in your engineering classes, okay? So let's get to our slides for today. And right here. See, bring it up. And we stop here, physical construction of the capacitor. And then we look at the voltage and the capacitor current. Voltage and current for the capacitor. So we established that the capacitor is basically storing the energy, right? The name capacitor itself comes from its capacity to store energy. And so Q equals CV is an equation we saw a couple of slides ago. If you take the derivative dq over dt with respect to time, changes with respect to time, this is nothing but current. Current is the rate of flow of charge. So if you take dq over dt, that automatically describes current I. So I can write an equation for capacitor current I in terms of the voltage or the time rate change of voltage. I equals C dV over dt. Is the exact same equation as we had for the inductor, except the quantities are flipped. For an inductor, we always talk in terms of an input current. And for a capacitor, we always talk in terms of an input voltage. So where inductor voltage was given L di over dt, here capacitor current is given as C dV over dt. Okay, exact same form for both equations, no difference. The notations may or may not be included, but the equations still mean the same. Okay, so for the inductor equations, I did not have the explicitly stated that it's a function of time. So whether it's stated or not, it still means the same. So this may or may not be included. When you read or when you attend different professors or different lectures, if you read different papers or journal articles or textbooks, the notations could be different. You could simply have I or IC or IL. Similarly, you might just have voltage. If it's just a single component, you don't specify anything. Or it could be described as a function of time, where I would write it as IC of t or VL of t. They all mean the same. Okay. The subscript might change depending on the circuit, depending on how many components you have. If you have multiple capacitors or multiple inductors in the circuit, you would go C1, C2, C3, so on and so forth. So, for example, this might be VC1 of T or IL3 of T. Simply refers to the inductor 3, L3, with capacitor 2, C2, or 1. So again, the equations still mean the same. They are not any different, okay? You don't need to write these down, except you should understand that, if you see as a function of time, I of t or V of t, with or without the t, it means exactly the same thing. Capacitor current, given C dV over dt, same thing as an inductor. Once it reaches full charge, meaning whether it receives energy from a voltage or a current, it reaches full charge. The voltage or current does not change anymore. It reaches a state of steadiness. That state is known as steady state. And at steady state, capacitor behaves like an open circuit because the current goes to zero. Right? If V is constant, dV over dt is zero. And so I, for a constant applied voltage, meaning DC, would be equal to zero. So for a steady state, capacitor acts like an open circuit. The inductor at steady state behaves like a short circuit. Remember, if current is constant, voltage across the inductor goes to zero. Di over dt would be zero for a constant value of the current. Yes.
Do you mean the current through the capacitor is zero,
Yes. Yep.
but only through the capacitor? So the other.
Yes. There still could be other elements. So if you have, if students have taken the lab in 251 and lab number 5, the last procedure, the last circuit, where you perform an experiment where you apply a DC voltage of 10 volts to an inductor and a capacitor. Capacitor is the far end or the far right side of the circuit. How many of you are taking the lab, by the way? Okay, almost all of you. Have you already done lab 5? Right? So you saw that in steady state, capacitor behaves like an open circuit. You don't include or account for that resistor voltage. There's no voltage drop across that resistor because capacitor reaches full charge. Open circuit, no more current is flowing through there. All of the voltage is across the inductor and the other two resistors because the inductor behaves like a short circuit. Just on a tangent, the inductors we have in the EE department, they're both of high quality as well as of low quality. So the ones that we use for these labs are of low quality. That's on purpose to show you that if an ideal inductor or a really good quality inductor should not have any voltage across it. But because these are low quality inductors, it has some DC resistance. And when you have a DC resistance in there, some of the voltage is dropped across that inductor. Okay. Anyway, coming back to our equations for capacitor. Since it's flipped now, we are trying to find the capacitor voltage if you're given the capacitor current. We simply integrate both sides. So you have I equals dV over dt. You integrate both sides. Go through the steps. Limits of the integral is 0 to t. You take c on the other side, so it becomes 1 over c. Simply stated, the voltage for a capacitor is integral of the I. You sum up the current over the entire time period of your analysis. And that's all it is. It's flipped. Again, it's the exact same form for the inductor. For the inductor, it was the current of an inductor is given by the integral of the voltage. For a capacitor, the voltage is given by the integral of the current. The form of the equation remains exactly the same. You're integrating from a time period t0 to t. And you also take into account any initial stored energy in that capacitor. And we will see that in one of the solved examples later on in just a few slides, actually. Okay. Equations for power and energy are also exactly the same. Electrical power is the product of voltage and current, V times I. You plug in the values and you simply get CV dV over dt. I is C dV over dt. You multiply capacitor current I times voltage. You simply add a V in that equation. So CV dV over dt. And then for energy, again, you integrate the power. So energy is simply half CV square. And this is simply the total energy that is stored in the capacitor. Okay, half CV square. For an inductor, it was half Li square, similar form, half CV square. No difference. That simply gives you the total energy that could be or was stored in the capacitor. Again, remember that voltage or current could have a fixed value. So you plug in the value and you have your answer. So then, before I move on, any questions?
The total energy.
Yes. Energy is basically the work that is being done. Can be described in many ways, but that's where the lowercase w comes from. Yes.
Voltage is a function of time. Right.
Yes. Voltage and current both are functions of time. Yes. All right. No more questions. Then let's move on to examples. So there are 4 examples in here. Examples 1 and 2 are rather straightforward. Just because I don't have time to go over everything, what I'm going to do is I'm going to go to straight examples 3 and 4. In 1 and 2, I will post either a video, I will write it down in a slide and include it in the class notebook as a handout. And there'll be, it's rather straightforward, not that difficult. We have V of t is given by 10 cos 6,000 t. And then here we have given I of t, exponent function e raised to minus 3,000 t. All we are doing at this point is doing a mathematical calculation. Okay. So again, I will post either a video or a slide and include it in the class notebook for examples 1 and 2. The important point to note, there are 4 examples in here. One of the actually 2 of the homework problems are similar to examples 3 and 4. And that's why I wish to cover that in class. Okay. But all 4 examples, 1, 2, 3, and 4 can equally apply to capacitors as well as inductors. All of these examples talk about a capacitor. And so capacitor, and again, a capacitor, okay? But they equally apply to an inductor also. It would not be any different, right? If you're given a capacitor voltage and you wish to find the current, you would apply the equation C dV over dt, take the derivative of the voltage, right? Similarly, if you wish to find the voltage, you would integrate this current. You're performing an integration of this function. That is not something new. As engineers in your own field, I would assume that you would have done this many times previously, right? Derivation and integration, calculus. And then for inductor, it would simply be flipped. Where you integrate for a capacitor, you would perform a derivation, and where you perform a derivation for a capacitor, you would simply integrate. Voltage and current is simply flip sides of both. Anyway, let's get to examples 3 and 4. How many of you have heard of piecewise linear analysis? All right, some of you, most of you, because it's a common technique in physics and science and engineering. And we also saw this earlier in superposition. You break up the circuit into smaller pieces And so that's what we're doing here. Understand that when you apply a DC signal, DC voltage or current to a capacitor or inductor, we know it's constant with respect to time. So we already know that at the end of the application, at some point in time, it will reach that value. If you apply 5 volts DC to a capacitor, for example, we know that the capacitor will reach 5 volts DC at some point in time, right? Same thing for a current for an inductor. We know that it will reach that maximum value at some point in time. We only need to find the values from the start point to the end point, and those values we will look at in chapter 4, right? In chapter 4. So the equations that we looked at here, not equation, sorry, the problem statement, this is a time varying input. Cosine is a function of time. Note, it's a function of time, meaning the value is changing with respect to time. It's not constant. And same thing here. Both of these voltages and current is a function of time. Again, if it's a DC, we already know what the value would be because it's going to be a constant. But this is a function of time. Some functions can be easily described. If it's a cosine or a sine wave, you can use sine or cosine. But if you have a graphical illustration like this, how do we describe it mathematically? And for that, we use the technique known as piecewise linear analysis. And what we are doing is, depending on the input signal, if it is possible, we would break it up into smaller individual pieces, and each piece would have a linear relationship with time. Again, it may or may not be constant with respect to time, but it should have a linear relationship with respect to time. The purpose is that in this technique, we can describe each piece as a straight line. Okay, straight line. In this case, if you look at this example, I can break up this into 2 individual pieces. And in both pieces, the input signal has a linear relationship with time. So the first time period, I'm going to call it as T1. T1 is between 0 and 6 milliseconds. Okay, time period 1, T1, is between 0 and 6 milliseconds. And I can see that that portion has a linear relationship with time. It changes, but it is linear. And so I can use the slope line intercept method to describe that line. We write a line equation. And there are various forms for this. M is slope, Y is T, X is T, Y in this case is V. And then this, of course, is the Y-intercept. But the beauty of using this for the capacitor current is that capacitor current is C dV over dt. We already have T on the x-axis. We have V voltage on the y-axis. If we describe the slope of that piece, we automatically have a value for dV over dt. Make sense? Right? And that's the beauty of this technique. The slope of this line directly gives us a value of dV over dt. All we have to do is find the slope, multiplied with the capacitor value, and that's it. That's all we need to do. So as a refresher, slope can be given by 2 coordinates. We take 2 points, find the coordinates, and simply plug in the values, and you'd have your answer for the slope for the first time period. So for T1, I will call that as M1. And I'll take the two endpoints. I would have 24 minus 0 volts and 6 minus 0. And do not forget the milli. It's milliseconds on the x-axis. Okay, you'd be off by a factor of 1,000. So 10 raised to minus 3, that's my slope. 24 divided by 6, give me 4. So the slope is 4 volts for every millisecond, or 4,000 volts for every second. Either ways, both answers are correct. And then I, capacitor current, would simply be given by C times M1. I'll call that I1 because we are in time period 1. So C times M1, simply plug in the value, and I obtain this answer. Okay, you solve that, and you obtain 20 milliamps. Okay, 20 milliamps. A general word of advice, a general piece of advice. As engineers, if you look at any job description, it'll always tell you a company look for detail-oriented candidate. Okay, detail-oriented candidate. So paying attention to detail is very important. The point I'm trying to make is when you look at a problem statement, you extract as much information as you can from that problem, whether it's from words or whether it's from an illustration as shown in this figure. In this case, it doesn't tell you anything except capacitor value is 5 microfarads, determine the current. It doesn't give you determine the current for the first time period or second or third, doesn't really matter. It just says find the current. So look at the information. This is a key piece of information is right there, this lowercase m. Obviously, as engineers, you recognize this as a unit prefix milli, 10 raised to minus 3. It is not stated anywhere else in the problem, but it would be your job as an engineer to pay attention to the small details and extract that information. Because if you do not have that milli prefix in your equation, then your answer would be incorrect. On an exam, it might just be like -1 or -2 points in a quiz or an exam. But in real life, if you miss this, well, if you're trying to design a system, the entire system could fail, right? So again, extract as much information as you can from the problem statement. And this is true for any course, any subject that you take. All right, so our answer is 20 milliamps. Similarly, if we plot it for the second piece, the second portion, our T2 is between the time period 6 to 8. So 6 to 8 milliseconds. My slope M2 is now going from 24 to 0. So it'd be 0 minus 24 and 8 minus 2 times 10 raised to minus 3. So this is minus 12 volts per millisecond, or 12,000 volts per second. Yes.
For the second term, you would have 8 minus 6, right?
Oh yeah, 8 minus 6, sorry. 8 minus 6. That gives me 2. Should take my own advice and pay attention to details. So I have I2 as C times M2. You plug in the values and you solve it. We should obtain 60 milliamps. 60 milliamps. Oh, minus 60 milliamps. Again, negative slope, right? Negative slope. And negative in this case simply implies the current is now flowing in the opposite direction. That's all. This capacitor is actually discharging on the other side. And you take those values and you plot it, because it's not a function of time, simply a straight line between those time periods. So between 0 and 6, it has a value of plus 20 milliamps. And between 6 and 8, it is minus 60 milliamps. And you plot it and you get kind of like a rectangular pulse. All right, 10-second pause. Think over that. Let me know if you have any questions. Does it make sense? Easy enough. So this one was finding the capacitor current if you were given the input voltage. The same example for an inductor would be, inductor current would be given to you, and you were asked to find the inductor voltage. You'd perform the exact same equation, you'd perform the exact same analysis. Find the slope, multiply it with the inductor or inductor value, and you'd find the inductor voltage. VL is L di over dt. So if inductor current is given to you, describe it in terms of, the slope of the line, multiplied with the inductor value, and you have the voltage. So again, goes back to that point on the previous slide that all 4 examples are the exact same and work the same for both inductor as well as capacitor. So that's the first one where you perform a derivation, right? Now let's look at the other side of this, where we integrate the voltage, we integrate the current to find the voltage. So the question here is that a capacitor of 4 microfarads is applied a current, or you're given the capacitor current in this graphical form. What is the voltage? Looking at the graph or the chart, I can see, actually I can see because I know that this is 8, but it's not that hard. It's minus 8 microamps in the second time period, and it is about 16 microamps in the first time period. We call this T1, and this would be T2. At T1 and T2. So time period 1 is from 0 to 2 milliseconds, and T2 is from 2 to 4 milliseconds. And beyond 4, it is 0. So we don't need to write T3, but I'm just, pointing it out that if there was a third one, we write the value until it goes to 0. Okay, what else do we have? We have 16 microamps, minus 8 microamps. T2 is rather straightforward. So let's tackle that first. Time period 2, and the reason it's straightforward is because it is a constant. It does not change with respect to time. It's a constant value. So I don't need to write an equation. Simply have the value, minus 8 microamps. Excuse me. Right, so again, understanding everything from the problem statement or the given information, that's the key. The second time period is a constant which has a value of minus 8 microamps. For the first one, M1, I will take, let's see, 16 microamps minus 0. So 10 raised to minus 6 divided by 2 minus 0 milliamps. So I would get 8 into 10 raised to minus 3 amps per second. Or I could do 8 milliamps per second. either ways. Okay, 16 microamps for 2 milliseconds. So it's climbing 16 microamps for 2 milliseconds or 8 microamps for 1 millisecond. And then y equals mx plus b. Equation for I is the slope times t. And b, of course, is 0. And that's my equation. That's my equation that describes the current for the first time period. Okay. The purpose of breaking it up into individual pieces is that each piece is linear with respect to time, hence the term piecewise linear analysis. So linear relationship 8 into 10 raised to minus 3 t. Then I can begin my calculation. Let's just focus here for now. What we want to do is we want to find the value of the voltage given that the input is current. The input current is given as a function of time, right? 8 milliamps, 8 times 10 raised to minus 3 t. It's a function of time right here, right? T. It basically means that equation describes the value of that current in the first time period. So when I go to find my voltage will also be a function of time. So the limits of the integral, we are summing up over a certain time period, right? You have a current that goes from 0 to 16 between the first time period 0 to 2. You're slicing individually and summing everything up. That is integration. So when you integrate, you have to specify the limits of the integral. Because it's a function of time, the limits of the integral will also be 0 to t. Actually, technically it is t0 to t. T0 is the point at which I begin my analysis. And in this case, the portion is 0 to 2. So T0 is 0 milliseconds. The time where I begin my analysis. Remember, I made this point earlier. You have multiple pieces, and you're analyzing each piece. The beginning point of each analysis is different. So for this analysis, meaning from 0 to 2 milliseconds, my T0 or the beginning period is 0. T0 is 0. So that's where this 0 comes from. So the limits of the integral are 0 to t for this reason. And then, of course, this variable x can be anything. A, B, C, D, E, F, G, whatever you wish to use. X, Y, Z is the most popular, so I just use X. Just to differentiate it from t. If you look at some books, they will continue to use the variable t in the equation, and the limits of the integral will also be t. So sometimes that's confusing. We have those in our EE books. I also want to make sure students understand that. Is that clear? Is the setup of the equation clear? Okay, from that point on, it's simple math. Well, not simple, but just math. So you plug in the values. V0 is the initial stored energy in that capacitor, the time at which you begin your analysis. At the beginning of our analysis, it was not specified whether the capacitor had any stored energy. If it is not explicitly stated in the problem that the capacitor had some initial value for the voltage, you assume it to be 0. All right. In the problem statement, it would be given. Otherwise, you can assume it to be 0. So in this case, V0 specifies the initial stored energy, in that capacitor. And since it's not stated, you simply assume it to be 0. So the only thing I have in here is 1 over C, which is 1 over 4 microfarads, and my equation, 8 into 10 raised to minus 3. Take the constant outside, and I would have 8 into 10 raised to minus 3 divided by 4 into 10 raised to minus 6. This would become x squared over 2. Limits of the integral is 0 to t. And you solve this. 2 comes outside, cancels everything out. All I'm left with is 10 cube outside. And you plug in the limits of the integral in there, and you get t squared volts.
No, C,
Sorry, where?
R1 over C.
This?
For our capacitance, we just reflect it when we're doing that.
Capacitance is right here. 1 over 4 microfarads. Are you talking about this or this calculation?
No,
Capacitor was stated as 4 microfarads in the problem. And so 4 microfarads is right here. 1 over 4 microfarads, 1 over C. 8, okay. All right, so our answer is 10 cubed times t squared. Again, it's a function of t. I'm going to move along. I have about 11 minutes left. So when you get to the second time period, now my second time period is from 2 to 4 milliseconds. So my T0 is 2 milliseconds. The time where I begin my analysis is 2 milliseconds. So T0 has a value of 2. So voltage at 0 for this would be the voltage of the capacitor when t equals 2 milliseconds. So it's not 0 for this time period, because for the second time period, there is a stored energy that comes from the first time period. Does that make sense to everyone? Right? And so we go back here, you plug in the value of t as 2 milliseconds in this equation, and then you solve and you obtain the value as 4 millivolts. And that is the purpose of finding that value, because that is the stored charge in that capacitor when you begin analysis on the second time period. Okay, and that 4 millivolts is taken into account in the second equation. So here is rather straightforward. Again, because it's a constant, I don't have to worry about anything else. I simply plug in the value, minus 8 microamps. It's a constant, you take it outside. So you get minus 8 microamps divided by 4 times 10 raised to minus 6. And note limits of the integral. T0 is 2 milliseconds. So it starts at 2 milliseconds and goes up to t, again, variable t. My start point for this analysis is 2 milliseconds. So it does not go from 0 to t, it goes from 2 milliseconds to t. You're integrating or you're summing up between 2 and 4. And then, of course, x dx. Actually, so it's just dx. Right, just dx. So you simply get x You plug in the values and you would obtain this expression. Minus 2t plus 8 into 10 raised to minus 3. Minus 2t into 8 raised to minus 3. It's rather straightforward as far as integration and differentiation go. Okay. Once you have your equations, you can plot them. In the old days, we would take a number of data points, simply calculate each and every value on a calculator manually, and you plug in t is 0.1, 0.2, 0.3, and so on and so forth to find the values. And now you have MATLAB, you have programmable calculators, you have Excel, you have software. You simply plug in the values, you plug in the equation, and you have your answer. Right? Very easy to do. Now, in a quiz or an exam, I would not ask you to actually plot this out. Not unless it would be like straightforward or simple. Okay. But hopefully everybody understands this, because you would have encountered this as an engineer in your own field, or you probably will in the future. Okay. All right, questions. Did it all make sense? Right. The setup of the problem is the most important. After that, the math is not something new. The math is something you would have seen before. The setup of the problem is the most important. Even the technique is something that you would have seen. At least some of you have seen. So one or two of the problems in the homework is exactly the same as this. You piecewise linear analysis. You calculate the values and you enter the values in the online in the homework. Okay. Any questions? Any questions before I move on? Okay. So if you have series or parallel connections of resistors, you know what to do. But now we look at series and parallel connections of inductors and capacitors. So if you have two inductors in series, and you try to find LEQ between the outer terminals, they simply add up similar to resistors. For a parallel combination, again, adds up the same way as resistors. So it's the reciprocal of sum of the reciprocals. 1 over L1 plus 1 over L2. Two capacitors in parallel. CEQ is simply C1 plus C2. And two capacitors in series, they add up the exact opposite. And so I can write okay. Inductors add up the exact same way as resistors. Capacitors add up the exact opposite. So inductors, you don't have to think too much. Capacitors, you do. You cannot combine a resistor with a capacitor. You cannot combine an inductor with a resistor. But if you do have two inductors, two or more inductors, you can reduce that circuit. If you have two or more capacitors, you can reduce those capacitors for the purposes of analysis. Okay. On the last slide, as I've been stated several times, it's a complete summary of all the equations that we looked at in this chapter. The last two equations right here are basically series and parallel connections, and everything else above is the voltage and current equations for both inductor and capacitor. You can have all of these equations in your equation sheet. The important thing is you should recognize them and you should know when and how to use them and apply them. All right, that is more important. So I would say this is the end of chapter 3. Chapter 4, we'll continue with capacitors and inductors, but we will look at transient analysis, specifically DC transient analysis. Remember, I said energy is either received or being sent out from the inductor and capacitor. Okay. So if you apply DC, we already know what the value is going to be, but we don't know what the value would be during the energy transfer phase. And so those equations are what we'll look at in chapter 4. Okay. All right, questions? Any questions at all? Everybody eager to go party? Or at least catch up on some sleep, like I plan to do. I need to get caught up on my grading also. So before I leave, a student actually last week asked me about some of the music, and so I thought I would share this. So I'm from India, in case you don't remember, and so I want to share this. This was from a Norwegian group. So let me just share this. They performed this at a wedding. Okay, this was in Norway. So it was started by a group of brothers from Norway, and along with their childhood friends. So 3 of them, they call themselves Quick Style. They performed on Norway's version, like Norway Got Talent. They also came to the US, India, Africa, all over the world they travel. They did this at one of the brothers' wedding. I think it was like a few years ago, 2 or 3 years ago. And it quickly became a viral hit. And so it spread all across the world, and people were like taking this song and the steps that they did, and they would do viral TikToks like in New York and DC, and that's just the US, but all across the world, you would have people recording similar steps and posting them on TikTok and YouTube. The original song for this is from an Indian movie, and the title of the song is Kala Chashma. It simply means Kala is black, Chashma is eyeglasses, so it's basically sunglasses. Kala Chashma is just dark sunglasses. That's all it means. So the song, it basically goes, you look really good in sunglasses. But it's become a very popular song, so something to get your party started for this weekend. All right, I'll bid you a good weekend. I'll see you all on Wednesday.
Thanks, Professor.